Hello and welcome to lecture 51. We are discussing about turboprop engines. In last lecture we were discussing about what we mean by say propeller. Then we were discussing about what all are the construction detail for the turboprop engine. Then we have looked at how these engines they are being placed on the aircraft, what all are the applications, what are the challenges and advantages of this turboprop engines. So in this lecture we will try to understand how do we analyze this single spool turboprop engine. So here if we look at this is representing single spool turboprop engine where we are having compressor. That compressor it is connected with the turbine. Similarly here we are having the gearbox and the gearbox is connected with the propeller. So if we look at in overall this turbine, that's what is used to rotate both compressor as well as the propeller, and that's the reason why we have defined that as a gas generator. So here we can see the construction of the single spool turboprop engine. This is the diagram for say T56 where we can easily see this is representing the compressor, combustion chamber, that's what will be followed by the turbine, and on the front side if we look at we are having the gearbox and that's what is connected with the propeller shaft. Here this also is representing TP331 Honeywell engine where we are having this as intake. Just look at carefully, that's what is supplying the air to the centrifugal compressor. This centrifugal compressor that's what will be supplying this compressed air to the combustion chamber, and here we are having say two turbine stages. These turbine stages they are connected with the compressor as well as it is connected with the gearbox, and this gearbox it is connected with our shaft. We have discussed about the configuration in which there is other possibility where our compressor that's what will be rotated by the separate turbine stages and the propeller that will be rotated by the turbine stages, what we say as a free turbine configuration. So here if we look at this is representing say PT6E engine. If we look at carefully the front side, that's what is representing my intake. That intake that will be followed by the axial and centrifugal compressor, that will be followed by say reversible combustor. Here we are having say turbines. This is representing the exhaust, and this turbines if we look at carefully, second turbine that's what is connected with the shaft, and this shaft that's what will be connected with the propeller, and we have defined that as a two spool configuration. So for today's lecture we will be focusing main on say single spool configuration. So just look at how do we analyze this engine. So let me put the stations. Suppose if I consider here it is a free stream condition or say atmospheric condition. Here we are having intake. That intake that will be followed with the compressor, combustion chamber, turbine, and we are having the nozzle. So let's try to understand say this process or cycle on TS diagram. So here we can say we are having atmospheric pressure from where the air that's what will be going inside the intake, and here this is representing my air intake, actual intake process, that will be followed by the compressor. So 2 to 3 that is representing actual compression process. Then we will be having say rise of pressure as well as temperature because of addition of heat through combustion chamber, and it will be attaining the maximum temperature, maximum cycle temperature, or we can say maximum turbine entry temperature or turbine inlet temperature. This is subjected to the expansion which is represented by process 4 to 5. It is representing my turbine process or turbine expansion process, and later 5 to 9 that is representing my expansion which is happening inside the nozzle. Now let me discuss, let me put the point here. Here in this case if we look at, we can see we are having expansion that is happening in the nozzle. That may or may not be the case. It depends on what kind of application we have, what kind of engine we have designed, what is the requirement by the aligned companies, or maybe what is the application of my engine. So majorly thrust will be generated by the propeller only. The expansion what all we are looking for may be of very small amount, maybe 5% to 10% only, that will be happening inside this. Okay, so majorly the power consumption, that's what is happening, is for rotation of our propeller as well as the compressor. So just try to analyze. So we will be analyzing this engine in both the way, where we will be having say thrust that will be generated by the nozzle, and we will not be having thrust generation by this nozzle. Okay, it's a special kind of applications. Otherwise you feel this is like what all we have discussed in terms of turbojet engine. So this analysis is somewhat different. Let's try to understand that part. So very first component what we have is our intake or say inlet. As we have discussed, these intakes are of different kind compared to our turbojet engine as well as turbofan engine. They are of specialized kind of intakes. Okay, for that the diffuser efficiency we can represent or we can write down in terms of say isentropic say enthalpy drop divided by actual enthalpy drop, and here we can calculate what will be our outlet pressure, outlet total pressure from the diffuser, and outlet total temperature from the diffuser. So this is common for what all we were discussing about gas turbine cycles. So it says like intake, that's what is different here, and what efficiency we are discussing, that's what will be slightly lower compared to what all engines we have discussed up till now. Let's move towards the next component we have. It is say compressor. This compressor may be of axial kind or maybe axial centrifugal combination, or it may be only centrifugal compressor. It depends again what kind of engine we are configuring. So here in this case, let's say suppose if I consider we have multi-stage axial flow compressor. So the efficiency, that's what we are representing in terms of say pressure ratio and polytropic efficiency. We can calculate our say pressure, outlet pressure from the compressor by using say temperature ratio correlation, both in terms of say efficiency as well as compression ratio. We are able to calculate what will be the exit pressure and exit temperature from the compressor. Now let's move towards the next component. The component we have is our combustion chamber, and for this combustion chamber we can draw the control volume. Here this is representing the amount of heat what we are inputting inside the combustion chamber, or we can say the amount of heat, that's what is added or coming out from our say compressor. So it is given by m dot core into H03. This is representing our mf into cv, that's what is representing the amount of fuel what we are adding. That amount of fuel, that's what will be converting the chemical energy into thermal energy, and we will be having our exhaust as m dot core plus mf into H04. So here in combustion chamber we will be having drop of pressure as we have discussed earlier also. Now if I'll be writing my energy balance, by that way we can calculate what will be the fuel air ratio for this combustion chamber. So this fuel air ratio, we can say we are able to calculate what will be the value of F. So here again let me put the point, say in order to achieve that particular temperature you can calculate what is your fuel air ratio, or other way maybe if you know what is your fuel air ratio, you can calculate what will be your turbine entry temperature. So do this calculation or do understand that in both the ways. Now what is the kind of fuel we are using, that also matters a lot in terms of what is my fuel consumption. Okay. Now let's move towards the next component, that's what is say our turbine. Now as we have discussed, this turbine is we say it is a gas generator. So let's try to understand what exactly is happening in the construction, or how do we analyze this cycle here. We know these components are mechanical components and they are generating the mechanical power. When we say mechanical power, we will be having, say, bearings. They are connected in order to have the rotation. At the same time, we will be having some losses because of friction, mechanical friction, and that's the reason why we will be having the terminology, that's what we say as a mechanical efficiency. So just look at here. Suppose if I consider this is the station where I am having this turbine and the compressor, they are connected with the common shaft. So power transmission that we can representing in terms of, say, mechanical efficiency of the turbine into work done by the turbine. That's what we are supplying to our, say, compressor. Suppose if I consider my next station, that's what is between my compressor and the gearbox, then my power transmission will be what power we will be getting from the turbine minus some amount of power, that's what will be consumed in the compressor. And this we are representing in terms of compressor work divided by mechanical efficiency. Many times we are considering only mechanical efficiency as a term. We have done this kind of calculation earlier also, where we are considering mechanical efficiency between, say, compressor and the turbine. Now next, if we look at what power I will be getting from this gearbox, that's what is being used in order to rotate the propeller. Since this gearbox also is a mechanical device, and that's the reason it will be having mechanical losses, and those losses we are counting by incorporating gearbox efficiency. So ultimately the amount of power which will be available at the propeller, that's what can be represented as a propeller efficiency into gearbox efficiency, and this is what is the amount of power, that's what will be generated during my initial stage. So you can say this is how my power transmission, that's what is happening. Let me put the point here. Now in order to rotate this compressor, what is the amount of power requirement, and in order to rotate propeller also, what is the amount of power requirement, that is little tricky in sense of calculation. Suppose say I am having all the properties, aerodynamic properties of this propeller, that's what is available. From that, if by some means I will be able to calculate what is the power requirement, then by addition of that power we can calculate where my point 5 will be located with. But at this moment, suppose say we are not having that kind of configuration available with us. What do we do? Here in this case, we will be considering this delta H. This is nothing but the delta H is here. This is representing my delta H. This delta H is nothing but my ideal process, or say isentropic expansion process, that's what is happening both in turbine as well as for the nozzle. Okay, because we are not aware of what will be my delta H here. Now let's try to understand how do we analyze this kind of situation. So for turbine, as we have discussed, we are having delta H, that is total enthalpy which is available with us. Out of that, suppose if I consider the enthalpy drop which is happening inside the turbine, I am putting that as say alpha into delta H. So what will be the remaining portion? That's what will be 1 minus alpha into delta H. That's what is enthalpy drop which is happening inside my nozzle. Okay. Now the situation is what delta H we are representing. Basically this is my isentropic correlation, and suppose if I consider based on my energy equation, I can write down Cp delta T0, and here this is what is represented in terms of isentropic pressure ratio. Suppose if I know what is my pressure, atmospheric pressure, I have already information about my say inlet pressure. Based on that, we can calculate what will be the value of delta H. Now let's try to look at what do we do for the nozzle. We have information. Suppose if I consider, we have discussed for all these components, very important parameter, that's what is my efficiency. So for all the components we are assuming our adiabatic efficiency, or we say isentropic efficiency. Suppose if I say for intake, for compressor, for combustion chamber, for turbine, even for the nozzle. So let's use that fundamentals. So based on the definition of nozzle efficiency, we can write down the exit velocity from the nozzle. That's what is represented by 2 delta H nozzle efficiency into 1 minus alpha. Okay, you can do the balance of this. Okay, so I'm sure you will not be getting confused from where this relation is coming. You can recall what all we have discussed in week 2, that will help here. Okay, now let's try to understand the terminology. That's what we say as a propeller efficiency. So if you recall, in our first week we were discussing about this term. What we mean by propeller efficiency is thrust power generated by the propeller divided by our shaft power, and this thrust power we can say it is V infinity into thrust that will be generated by the propeller divided by my shaft power. So what is my output and this is my input. My input is shaft power. That's how we need to understand this term. Similarly, we may be having the equation for say thermal efficiency. What we mean by thermal efficiency is say what we are getting in terms of our output, that is my shaft power output divided by my input is MF into CV, that is nothing but my heat addition. Now let's try to look at how do we calculate the thrust generated by the propeller. So this thrust generated by the propeller, that's what can be represented in the form of say propeller efficiency, gearbox efficiency, and this is our shaft power. So this shaft power we can write down in terms of this equation. Now what we know, what is the power available at the propeller? If you recall, previously we have come up with the equation. It says it's a function of propeller efficiency, gearbox efficiency, mechanical efficiency of both turbine as well as compressor, and work done. So let's try to get that equation. This shaft power we can write down in terms of this formulation. What we mean by shaft power here, it is by turbine minus this is what will be my compressor power consumption. This delta HT that we are writing in terms of say my turbine efficiency into alpha delta H. If we will simplify this formula, then we will be having thrust generated by the propeller. That's what is a function of all these terms. Okay, so just remember here this calculation, it is different from what all we have done up till now. Suppose say I am having contribution from nozzle also. So suppose if I consider some amount of thrust that will be generated by the nozzle, then this nozzle thrust can be written as same way. This is nothing but m dot infinity into 1 plus f V exit minus V infinity, or we can say V9 minus V infinity. So I am having thrust that will be by propeller as well as by nozzle. So let's try to put, we can say my total thrust that is given by propeller thrust plus nozzle thrust. Let's put in this formulation m infinity I am taking on the other side. Okay. Now here in this case we have information about say V infinity, or what we say V exit. V exit we are writing in the form of 1 minus alpha. So let me rewrite the formulation. So the thrust generated by turboprop engine by incorporating both the thrust contribution by propeller as well as nozzle, this will be my equation. Now the question will come here, sir, what we mean by alpha? How to decide that alpha? Okay, so in order to get that value, what we will be doing? We will be differentiating this equation with alpha, and that's what will be giving me maximum amount of thrust which will be generated by this engine. So let's look at this. So this is what is our formulation, and if we will be differentiating and we will be getting the calculation for the optimum value of alpha, that's what will be coming in this formulation. and from that we can calculate maximum thrust, that's what will be generated by this engine. Okay. Now this is representing what will be the exit velocity. So here if you look at all this multiplied by our V infinity, that number it depends on like it will be coming little less, or maybe as per your requirement you need to decide with what exit velocity you are looking for. So we will be solving the numerical where we will be having that kind of understanding in which we want thrust to be generated by nozzle also, and we will try to solve the numerical in which we don't want the thrust that be generated by my exit nozzle. Okay. So do not get confused here. This is what is a straightforward calculation. So this is my performance parameter, you can say, for earlier engines also, both for turbojet and turbofan engine. We have discussed very first term, that's what is my thrust. The next terminology what we have is in terms of say overall efficiency, or we can say thermopropulsive efficiency. In very first week we have discussed the overall efficiency for turbojet, turbofan engine. We can say this is nothing but it's my propulsive efficiency into thermal efficiency. There are open literature where says like overall efficiency of the turboprop engine that need to be calculated based on propeller efficiency and thermal efficiency. There are some literature where they are not considering the propeller efficiency, they are calculating propulsive efficiency and thermal efficiency in order to calculate the overall efficiency. So let's look at what we mean by this propeller efficiency. As we have discussed, suppose say I am having the thrust to be generated only by propeller, then we can write down my propeller efficiency is V infinity into T, that is by my propeller, divided by shaft power. Now let's try to understand the terminologies here. Say if we consider this engine, it is under static condition or nearly under test bench or say takeoff condition. So equivalent thrust power, that term let me introduce here. If you recall, in first week we have introduced this term where it says when we are having sufficient amount of thrust, that's what will be generated by the exit nozzle, then we need to go with equivalent thrust power, otherwise shaft power it is sufficient. Okay. So this is representing this thrust power because of both propeller as well as the nozzle. So here we are putting the terminology, it says equivalent shaft power, it is equivalent thrust power divided by propeller efficiency. Let's try to get the new formulation. It says equivalent horsepower. So British unit people they are using many times in order to do the calculation. Conventionally in market people they are discussing in terms of say horsepower also. Few companies, few engine manufacturers, they are discussing in terms of kilowatt also. So here if we look at, it says shaft horsepower plus shaft horsepower equivalent to net jet thrust. Okay. Now in order to calculate this thrust that is generated by the jet thrust, it says we need to consider 1 kilowatt equivalent to 8.5 Newton of say jet thrust. So let me put this equation. It says equivalent power, thrust equivalent power for the takeoff, it is given by shaft power in kilowatt plus jet power in Newton divided by 8.5. Okay. And here in this case jet thrust we can calculate as we have discussed in terms of m dot into 1 plus f V exit. Okay. Now let's move towards the next terminology. So here in this case we are having the term, it is called say thermal efficiency. This thermal efficiency, if we are taking the contribution because of equivalent thrust power, then we need to calculate the thermal efficiency not based on shaft power, but we need to consider equivalent shaft power. Do not get confused here. It's specifically been mentioned if we are having the contribution because of engine exit or the thrust it is generated by engine exit also or by nozzle also, then in place of shaft power we need to take equivalent shaft power divided by mf into qr. Okay, and here this equivalent shaft power, that's what is given by shaft power plus T into V infinity divided by constant into say propeller efficiency. Now this is what is related with the flight condition, that is very important. Okay, so let's try to understand what we mean by this constant. So this constant, it says it is depending on what kind of flow configuration we are selecting with. This constant, let's put, suppose if I consider equivalent shaft horsepower, if I am taking that in pound and miles per hour, then the equation will be like this. In denominator, we will be having constant as 375. Suppose if I am considering in pound and knots, then the denominator constant will be 325. And if we are having say pound and foot per second, then we will be considering that as say 550. So these all are the formulas in order to calculate equivalent shaft horsepower. Now usually this propeller efficiency we are assuming to be 80%. That's what is a common practice. If you will be having, say you are able to have your propeller efficiency to be calculated by testing or by design, that number you can select here. Okay. So there is one more terminology, very important terminology, that's what we are bothering of, is specific fuel consumption. So here in this case for turboprop engine, we are putting that as equivalent specific fuel consumption. That's what is given by m dot f divided by equivalent shaft horsepower. And it says typically that is in the range of 0.45 to 0.6 pounds per hour per HP, or sometimes in terms of our SI unit, they are taking 0.27 to 0.36 kg per kilowatt hour. So if you compare these numbers are higher compared to what all. But the thing is here, this is not related with the thrust. This is what is related with the shaft power. Be careful. Okay. So equivalent specific fuel consumption, conventionally for industries, they are calculating based on this equation where it say A plus B m infinity into square root of theta. This theta, as we have discussed, it is a ratio of ambient temperature at particular flight altitude divided by standard reference temperature. We know this standard reference temperature, we are considering 25 degree centigrade. Okay. And these constants A and B, they are 0.2 and 0.9 for our turboprop engine. If we are using this for high bypass ratio engine, it will be 0.4 and 0.45. Okay. Now, after understanding this, we must solve one numerical for the practicing, and that's what will build the confidence in terms of doing the cycle analysis. So let's take one numerical. It says the concept turboprop engine with the single spool configuration is undergoing for ground testing at sea level. The ambient temperature and pressure, they are 288 Kelvin and 1 bar. The test engineer registered the following particular. It says the core mass flow rate is 15 kg per second, compressor pressure ratio is 10, turbine entry temperature is 1200 Kelvin, the pressure drop in combustion chamber is 2%, exhaust jet velocity is 260 meter per second, the calorific value of the fuel is 43 megajoule per kg. There are different component efficiencies are given. Say adiabatic efficiency of the compressor to be 87%, combustion chamber efficiency is 98%, mechanical efficiency is 98%, turbine efficiency is 90%, combinedly gearbox and propeller efficiency is 75%, nozzle efficiency is 95%. We need to evaluate the performance parameter of this engine. Now here it is clearly mentioned we are having single spool configuration, that means this configuration is with gas generator. Okay. And on this side you can see this is what is representing our diagram, and you can start solving this numerical. Okay. So here we are stopping with. We will be discussing the solution of this numerical in next lecture. By that time you have sufficient amount of time, just try to calculate, and later on after discussion just try to compare. That's what will be building the confidence for you in order to solve such kind of numericals for say turboprop engine. So here we are stopping with. Thank you very much.